Hey, welcome back AP Calculus students. Today we're looking at 7.2 antidifferentiation by substitution, also known as U substitution. This is part one. We're going to spend 2 days on this because it's an important means of doing the antiderivative of a function. A lot of times we're not going to have nice, easy antiderivatives that come directly from our cheat sheet. So we got to be aware that we can do more complex ones as long as we're aware of our strategies that we can use. So the idea about U sub is just the reverse of chain rule. So remember when chain rule came out in first semester, we were doing derivatives and it was a little bit complex because we needed to remember that when we have an inside function and we do the derivative outside, we need to also do the derivative of that that inside function. It's the same thing but in reverse. So just kind of keep that in mind as we go forward. This first part, it's saying that f of x is equal to x squared plus 1 and u equals x squared. So they're trying to demonstrate here the difference between each of these three antiderivatives. Now the antiderivative of f of x dx is pretty straightforward. We're just going to find the antiderivative of x squared plus 1, which is going to be x cubed over 3 plus x, right? We're just using the power rule on both of those parts. We're also going to add in our plus c just to make sure that we have that's the general antiderivative. Now the second part is a little bit different, right? Because now we're doing f of u. So instead of having an x squared there, x there, we're going to have a u. So we're going to do the u squared plus 1, right? And we're finding the antiderivative with respect to u, or sorry, du, right? And so then we just go about that the same way, right? We're going to get u cubed over, did I write that wrong? Let's roll with it. Okay, so we're going to get u cubed over 3 plus u, right? And then we're going to go back and substitute our x at this point. So then we're going to do x squared cubed over 3 plus x squared plus c. And then that becomes x squared to the third. Power rule means we're multiplying our exponents. So power times power to a power, that's going to be x to the 6th over 3 plus x squared plus c. Okay, so notice because we're doing u with respect to u, that we had to put it in terms of u first, then do the antiderivative with the u in there, and then we plugged in our x at the end. Okay, so for this last one, this one is doing f of u with respect to x. So what we're going to do is we're going to make our u first. Our f of u is going to be u squared plus 1. But because we're doing it with respect to x, now we got to plug that x back in, or whatever our u would be in terms of x. So this would be x squared squared and then we can simplify the x squared before we do our integral. So that's going to be x squared to the second power is x to the 4th. And now we have it in terms of x. Now we can do our antiderivative with respect to x. So this is going to be x to the 5th over 5 plus x plus c. So notice how differently each of these three came out because we're deriving with respect to a certain variable. Okay, the next one, now we're getting to the u sub part. The important thing to remember with the u sub part is we're looking for the inside function. The inside function is going to be our u. And we're hoping that we have our du someplace on the outside. So du is outside. someplace outside of our function. Okay, so what we're trying to do is we're trying to do this so that we have e to the u du. Because we know that if we can find e to the u du, that's just going to be the derivative, the antiderivative, which is e to the u. Now, the tricky part is we need to have this du exactly like we want it to be so that we can do our antiderivative and not have that messy part. That messy part's going to just derive out. Okay, so let's change colors here. So in this case, our u, our inside is going to be this cosine x, so cosine x. Our du, the derivative of cosine x, is going to be negative sine x dx. Okay, so notice what we have on the outside here is sine x dx, right? Which is almost like it, but it's not quite like it. But there's a trick to balance this out. So we're going to rewrite this as exactly what we want. We want negative sine x dx. So negative sine x, we have e to the cosine x dx. Now, in order to balance this negative we have on the inside, we're going to put a negative on the outside. So notice we're not changing this value of our function at all. We're just rewriting it so that it fits our du. In order to balance that negative out, we put a negative on the outside so that it's positive sine x e to the cosine x technically, right? The double negatives are the same thing as positive. Okay, now that we have it in this form, that negative is not going to go away on the outside. It's going to stay as it is. But now we have sine x dx. So let's rewrite this in terms of u. So this is going to be e to the cosine is u. And then negative sine x dx is our du. Right, so this whole thing simplified to be du. Now the nice thing here is that we can find the antiderivative here, and then the du is going to be gone when we do our integral. So this is just going to be e to the u. This negative still stays there. And then now we can substitute back in our u. So this is going to be negative e to the cosine x. So that's kind of the beauty of u sub. It takes something that's complex and makes it a bit simpler when we do our integral. And it doesn't work in every situation, but there are many situations where it does work. And if it doesn't work, then we have another strategy we'll talk about a little bit later in this unit. But for now, let's just get really good at u subbing. Okay, next one. This one surely looks complex. We have a square root function, well, we have a square root portion of our function, and then we have an x squared. Now, we're going to use this inside part as u. So u is equal to 5 plus 2x cubed. Then our du is going to be, well, the 5 is going to derive out. The 2x cubed's derivative is going to be 6x squared dx. Now, as long as our variables match up, then we can work around that. So we can use this one even though the x squared part is not the same because the du has the 6 in it. So let's rewrite this. We're going to rewrite our integral exactly like we want it with our u and du. Okay, so we're going to say we want it to look like 6x squared. And then rather than put this square root thing, I'm going to make that a rational exponent, because it's going to be easier when we start doing our antiderivative. So the power is 1, the root is 2, and we have our dx here. Now notice this doesn't look exactly like this, so we're going to balance it out. What we're going to do is we're going to put 1/6 outside. And the reason we do that is because if we multiply 1/6 by 6, we get 1, and that's the exact same thing as our top equation, right? So we need to make sure we balance it out in that way if we have some constant that we need to add in to make our du perfect. All right, so let's write this in terms of u now. So this 6x squared dx is our du. And then we have this is our u, right? So we have our u to the 1/2 du. Don't forget your 1/6 outside. And then now we can do our antiderivative. This is a power rule, right? So we're going to do the power rule. U to the 1/2 plus 1 is 3/2 over 3/2. Du is gone, right? Which means that the 6x squared dx part is gone as well, right? Technically. So this is 1/6 times u to the 3/2 over 3 divided by 2. Let's make this a little bit simpler. Anytime we have a complex fraction, remember we can multiply by the reciprocal of the denominator. So 1/6 times the reciprocal of 3/2 is 2/3. This simplifies. So we have 1/9 u to the 3/2, and at this point we can plug in our u, which is 1/9 5 plus 2x cubed to the 3/2 plus c. Okay, and then there you have it. It's not too bad, but once you get the eye for it and realize that we gotta recreate our du and balance it out, then the u substitution stuff becomes a little bit easier. Okay, on to the last one. Fortunately, we do have a integral for cotangent on our cheat sheet. So this is going to be ln sine x. But what we do need to do is, so let's say that our u is 7x, right? That's our inside function. Then our du would be 7 dx. Right? The derivative of 7x is 7. Okay, so we just need to balance this out. So we need to make sure we do the integral. We have the 7 in front. Cotangent 7x dx. We're going to balance out that 7 that we put in, because we need our 7 in there for our chain, with the 1/7 outside. 1/7 times 7 is 1. Now, this part is our du. So let's rewrite this as the integral of cotangent u du. And then when we do our integral from our cheat sheet, it's going to be the integral of cotangent is going to be ln sine x, ln absolute value sine x. So this is going to be 1/7 ln absolute sine u, technically, right? Plus c. And we can substitute back in our 7x for our u. And then we're done. All right, so just a quick review. U substitution is the reverse of chain rule. All right, so when we're chaining, we have the inside function and we have to do the derivative of the inside function. All right, so when we're using U substitution, we're hoping that the chain part, the du part, is at least partially inside of our function, so that when we do our antiderivative, it disappears. It I don't want to say cancels itself out, but it anti-derives out. So it's just the reverse of chain rule. We're gonna have one more section on this. We're gonna work through it, and hopefully you guys get a good idea of how it works, spending 2 days on it, and then we can hopefully master chain rule so that you guys can do it whenever you're called upon to do so. Okay, good job.